Hi there, this is Heath. We're starting week 7. This is the introduction to eigenvalues and eigenvectors. Before we start talking about these topics, though, I'd like to review a couple of topics that we covered before spring break. We talked about determinants. Let's find the determinant of this matrix here. The first thing we will do is assign that matrix to some variable. And then we will row reduce this matrix. The first entry where I would like to get rid of is this 3. I have to use a 2 to reduce that 3. The lowest common multiple of these two values is 6. And so I'm going to take row 4 times 2 minus row 1 times 3. And that will become the new row 4. When I do that, 6 minus 6 will be 0. 10 minus 9 will be 1. 10 minus 12 will be minus 2. And 4 minus 3 will be 1. 0, 1, negative 2, 5. And this step caused a determinant to go up by a factor of 2 because the row that we were changing got doubled. And so now this determinant is equal to 2x. But this column is now in echelon form, which means we can eliminate its row and its column, but the 2 at the intersection comes out to the front. So 2 times the determinant of 0, 1, 3, 1, negative 2, 5, 1, negative 2, 1 is equal to 2x. I don't like having a 0 up here, so I'm going to exchange these two rows. And that gives me the matrix 1, negative 2, 5, 0, 1, 3, 1, negative 2, 1. On the left side, I still have 2 times the determinant. But because this step changes the determinant by a negative sign, the right side will now be negative 2x. Now I would like to eliminate this 1. I'll take row 3 minus row 1. That will become the new row 3. That gives me the matrix 0, 0, 1 minus 5 is negative 4. On the left side, we still have 2 times the determinant. On the right side, because this step did not change the determinant, we still have negative 2x. This column is now in echelon form, so we can eliminate this row and this column. The 1 comes out to the front, but that doesn't change anything. We still have 2 times the determinant. 1, 3, 0, negative 4 equals negative 2x. Now that we're down to a 2 by 2 matrix, we can take the determinant just by multiplying the diagonals and subtracting. We get negative 4 minus 0. And so negative 8 equals negative 2x, and therefore x is equal to 4. And so the determinant of this matrix is 4. Another topic that we looked at before break was the idea of alternate bases for vector spaces. Let's look at these two vectors, show that they form a basis for R2. To be a basis, for Rn, regardless of whatever value n is, we need n linearly independent vectors. In Rn. So we have the right number of vectors. The other thing we have to check for is that these two vectors are linearly independent. And we can test that by putting the aggregated matrix into echelon form. So I will eliminate this 3 by using the step row 2 minus 3 row 1. 3 minus 3 gives me 0. 1 minus negative 3 gives me 4. And I have a leading entry in the top row and a leading entry in the bottom row. Every column has a leading entry. And so these vectors are linearly independent. Running into the logo now. And so we have the right number of vectors. We check that they are linearly independent. And so we have shown that this is a basis for R2. Since it's a basis, we can use this basis to represent points using alternate coordinates. And so the question I want to ask here is, if I have the vector 2, 5 in the alternate coordinate system, how do we find the standard coordinates of U? Anytime we want to go from the alternate coordinates to the standard coordinates, all we have to do is work out a linear combination. This is the easy direction. Because these 2 and this 2 and 5, they don't represent 2i and 5j. They represent 2 of these and 5 of these. And so we can just figure out what that is. 2 of the first vector and 5 of the second vector is, well, 2 times 1, 3 is 2, 6. And 5 times negative 1, 1 is negative 5, positive 5. And that adds up to negative 3 and positive 11. And those are the standard coordinates of U. On the other hand, if we're given a point in standard coordinates, and we would like to find the alternate coordinates for that U, if we want to go from standard to alternate, that's not as easy. This is the harder direction. Because I don't know how many of these vectors or how many of these vectors will be needed, but I do know that once I find the right number of each of these vectors, the answer will be negative 2, 6. But this is a system of equations. And we can solve that by row reduction. So if I look at this system and row reduce it, I'll eliminate this 3 using row 2 minus 3 row 1. 3 minus 3 will be 0. 1 minus negative 3 is 4. 6 minus 6 is, that should be a negative 2 because it was a negative 2 up here. 6 minus negative 6 is 12. Divide this row by 4. 0, 1, 3, 1, negative 1, negative 2, and then finally eliminate this 1 up here. Row 1 plus row 2, 1, 0, negative 2, and 3 is 1. And so x is 1 and y is 3. We can check this by substituting this back in and seeing if that actually works. If I take 1 copy of 1, 3 and 3 copies of negative 1, 1, what's the total? In the top row, we have 1 and negative 3 is negative 2. And in the bottom row, we have 3 and 3, which is 6. And so that checks. And so the alternate coordinates of UB are 1, 3. Another thing we talked about before spring break were the idea of column space and null space and row space. If I have this matrix and I want to find the row space is the same as the column space of the transpose. And we transpose the matrix by writing the rows going straight down instead of going across. And so the first column becomes 1, 2, 4, and the second column becomes 1, 3, 7. And we can find the column space by just spreading this matrix out into 2 separate vectors and taking the span of those 2 vectors. On the other hand, if the question asked us to find a basis for the row space, basis has to be linearly independent. So are these 2 vectors linearly independent? They are, because the second vector is not an exact multiple of the first vector. And therefore these vectors have to point in 2 different directions, and that makes them linearly independent because they will span a plane and not a line. And so the row space is the span of 1, 2, 4 and 1, 3, 7. But the basis for the row space is just a set 1, 2, 4 and 1, 3, 7. The basis does not include the word span. Span takes these vectors and adds to the set all of the possible linear combinations we can form, and that's what creates a subspace. It's not a basis anymore once you write the word span. I want to mention a few theorems before we move on. For any matrix, the rank of the matrix and the rank of the transpose of the matrix are the same. The rank is the number of leading entries. In the echelon form. It's also the same as the number of bound columns in the echelon form. Or the number of linearly independent columns that we can find. And it turns out that this number doesn't change if we transpose the matrix. And so the size of the column space and the size of the row space are linked together because they have the same number of linearly independent columns. Let's look at this theorem. If we have an m by n matrix with rank k, let me give you an example. We have a 5 by 6 matrix with rank 4. 5 by 6 means it's 5 rows, 6 columns. And rank 4 means that 4 of the columns have leading entries in the echelon form, but 2 of the columns are free columns. Maybe not the last 2 columns, but 2 of the columns are free columns. In order to form a basis for the column space, I drop the free columns and keep the bound columns. And so the column space will only be 4-dimensional. It's a 4-dimensional subspace, but the columns have 1, 2, 3, 4, 5 entries in them. And so it'll be a 4-dimensional subspace in R5. I'm going to move down and look at row space now. When I transpose this matrix, because of this theorem up here, the transpose matrix will also have a rank of 4. It will have 6 rows and 5 columns, and 4 of the columns will have leading entries, and 1 of the columns will be free. And so the row space will still be 4-dimensional. But the row space will be made up of these vectors, and these vectors have 6 numbers in them. And so it won't be a 4-dimensional subspace in R5, it will be a 4-dimensional subspace in R6. And so while column space and row space are both 4-dimensional in our example, the column space is in R5 and the row space is in R6. The oddball space is the null space, because the null space is not based on the rank, it's based on the number of free columns. And so the null space will be a 2-dimensional subspace in our example. In other words, an n minus k dimensional subspace. And when we write out the null space, we have to incorporate all of the variables in our definition of null space. And there's a variable for every column. And so the definition of the null space will have to have 6 equations in it, which means it will be 6 rows in the matrix. And so this will be a 2-dimensional subspace in R6. And so that's where the Rn comes from. It will be R6 and not R5 because I have to account for every variable when I write out the null space. At this point, we're ready to start talking about eigenvalues and eigenvectors. We're going to start with an example. I want to look at this linear transformation. My linear transformation is based on the matrix 4, 1, -2, 1. And the question says, what does this transformation do to the standard basis vectors in R2? What happens to I and what happens to j? Well, the transformed version of I is just a times I, which is 4, -2, 1, 1, multiplied by 1, 0. We can solve this using the column row rule. So the 1 goes with the first column, and 0 goes with the second column, but that just equals 4, negative 2. And you should have known that because the standard matrix tells us what happens to I, and the second column tells us what happens to J. So we didn't actually have to do these calculations. We could have just said the first column tells us what happens to I, and the second column tells us what happens to J. So if I try to draw this transformation, here are my vectors I and J. They transform. I transforms into the vector 4, negative 2. And J transforms into the vector 1, 1. Both vectors have changed magnitude. I has changed magnitude by a lot. J has also changed magnitude. This one has a length of 1. This diagonal has a length of square root of 2. And they both change directions. And so both vectors changed in magnitude and direction. Let's work with the same matrix, but with a different basis, not the standard basis I and J, but this alternate basis, B1 and B2. What does the transformation do to these vectors? This time we'll have to calculate this out. T of B1 will be 4, negative 2 in the first column, 1, 1 in the second column, times 1, negative 2. That's 1 times 4, negative 2, plus negative 2 times 1, 1. All right, this is 4, negative 2, plus negative 2, negative 2. 4 and negative 2 is positive 2, and negative 2 and negative 2 is negative 4. And so this vector goes to 2, negative 4. Let's look at B2. The transform version of B2 is 4, negative 2 in the first column, 1, 1 in the second column, times 1, negative 1. So that's 1 times 4, negative 2, plus negative 1 times 1, 1, which is 4, negative 2, and negative 1, negative 1. 4 and negative 1 is 3. Negative 2 and negative 1 is negative 3. Positive 3 in the top row, negative 3 in the bottom row. But what happened to these vectors? This vector, 1, negative 2, looks like so. And it transformed into the vector 2, negative 4, which looks like this. B1 changed magnitude, but not direction. And look at B2. B2 started out as the vector 1, negative 1, and it turned into the vector 3, negative 3. It also changed magnitude, but not direction. So here's our definitions. An eigenvector of a matrix A, of a square matrix A, is a non-zero vector whose direction is unchanged by A. This means that A times X is an exact multiple of whatever X was to begin with. In this example, the transformed version of B1 is an exact multiple of B1 itself. In this case, the multiplier is 2. The transformed version of B2 is an exact multiple of B2 itself, but this time the multiplier is 3. So A of X is an exact multiple of whatever X was when we started with. For historical reasons, we use the Greek letter lambda to indicate the multiplier. And so an alternate definition, the one that you'll find in the book, is that X is an eigenvector of A if A times X and lambda times X are equal for some value of lambda. The value of lambda is called an eigenvalue. So in the last example, the first vector, B1 was 1, negative 2, is an eigenvector. And it's an eigenvector with an eigenvalue of 2. And the second vector is also an eigenvector, but it has an eigenvalue of 3. We require that an eigenvector has to be non-zero because the direction of the eigenvector is important and a zero vector doesn't have a direction. And only square matrices have eigenvectors. If the matrix is not square, then the transformed version of a vector will be a different size than the original vector, and therefore it can't be an exact multiple. So let's try some examples. Let A be this square matrix. We want to show that 6, negative 5 is an eigenvector of A, and we want to find what its eigenvalue is. So if I take this matrix and transform the vector 6, negative 5 with this matrix, this is 6 times the first column and negative 5 times the second column. 6 times 1, 5 is 630. And negative 5 times 6, 2 is negative 30 and negative 10. 6 plus negative 30 is negative 24. 30 plus negative 10 is positive 20. This vector and this vector are multiples of each other. This is negative 4 times the original vector. And so we transform this vector, and the new vector is an exact multiple of the vector we started with. And so the eigenvalue in this case is negative 4. So if we want to show that a vector is an eigenvector, we just apply the transformation and see what comes out, and what comes out will be an exact multiple of what we started with. Using the same matrix, let's show that 7 is an eigenvalue for this matrix, and find an eigenvector whose eigenvalue is 7. So we don't know what this eigenvector is, but there is some eigenvector that gets 7 times bigger? Well, we can multiply this out. This is the same thing as x times 1, 5 plus y times 6, 2 equals 7x equals 7x, 7y. Or x plus 6y equals 7x, and 5x plus 2y equals 7y. This is a system of equations, but I'm going to simplify it by combining like terms on one side of the equation. So I'm going to combine x and 7x, and you get negative 6x. And I'm going to combine 2y and 7y into negative 5y. So negative 6x plus positive 6y is 0, and 5x plus negative 5y is 0. Well, if 5x plus negative 5y is equal to 0, that's the same thing as saying 5x equals to 5y. So x equals y. And that's what this equation is saying. If I add 6x to both sides, 6x equals 6y, and so x equals y. So I just need a vector where x equals y. I can choose any vector where x equals y. Like 2, 2, or 7, 7, or negative 4, negative 4, except I can't choose 0, 0 because the 0 vector is not allowed to be an eigenvector. So we have to find an eigenvector whose eigenvalue is 7. Any vector where x equals y turns out to be a correct answer. Let's look at this last example for today. Let A be this matrix here. The number 2 is an eigenvalue of A. We want to find 2 linearly independent eigenvectors whose eigenvalue is 2, and then we want to write the corresponding eigenspace. So I don't know what the eigenvectors are, so I'm going to call them x, y, z for right now. And I'm going to multiply this out. 4, negative 1, 6, 2, positive 1, 6, 2, negative 1, 8, times x, y, z. Because 2 is the eigenvalue, the vector got 2 times bigger. And so the answer will be 2x, 2y, 2z. But this is the same thing as saying that x times 4, 2, 2 plus y times negative 1, 1, negative 1 plus z times 6, 6, 8 is equal to 2x, 2y, 2z. And if I bring the 2x and the 2y and the 2z over to the other side of the equation, here's what happens. The top row then becomes, instead of 4x, becomes 2x minus y plus 6z equals 0. The middle row, when I take 1y minus 2y, I get negative y plus 6z is equal to 0. The bottom row becomes 2x minus y. That was an x. This is an x. And 8z minus 2z is 6z equals to 0. Well, this is a very dull system of equations. When I row reduce it, the second row and the third row all cancel, and I only have one leading entry, y and z are both free. And so what we end up having here is the top row says that 2 times x1, 2 times x, is equal to y minus 6z. So in other words, x is equal to 1/2 y minus 3z. And if I substitute parameters for the free variables, then I get x is equal to 1/2 s minus 3t, where y is equal to s and z is equal to t. But this is the same thing as s times 1/2 10 plus t times -3, 0, and 1. These are my two linearly independent eigenvectors. The linearly independent eigenvectors, I'll write this a little bit more neatly. 1/2 10 and -3, 0, and 1. The eigenspace, because it's a space and not a basis, it is a span of those two vectors. -1/2 10, sorry, positive 1/2 10, and -3, 0, 1. Wow. Sorry that was a little messy. It's a little harder to do this with a 3x3 matrix. To summarize what we did, though, we multiplied the matrix times an unknown vector x, y, z. Because the number 2 was the eigenvalue, the answer is 2 times what we plugged in to start with. We wrote this out as a system of equations. On the right side, we had 2x, 2y, 2z, but when I brought the 2 over to the other side, these terms became 0. And in this example, all three equations became exactly the same, so that the echelon form had 2 rows of all zeros and 2 columns that were free. Because we had 2 columns that were free, we had 2 different vectors in our spanning set, and the eigenspace is a span of both of those 2 vectors. Next time, we're going to work a little bit more with eigenvalues and eigenvectors, and we'll talk about how do we find eigenvalues and eigenvectors if this piece of information isn't given to you at the beginning of the problem. That's next time. Thanks.